talk from quantum gravity experts. So we have the pleasure to hear from Astrid Eichhorn from the University of Southern Denmark, and she will tell us about the causal set approach to quantum gravity. The floor and the Zoom is yours.
Thank you, and thanks for the invitation and for making it possible for me to give this talk via Zoom. I will introduce the causal set approach to quantum gravity to you, and I would very much like you to interrupt with questions at any point during the talk if you have any, and I'll try to stop throughout the talk to ask whether there are questions to make it easier for you to interrupt me, but also don't hesitate to just jump in and ask if there's a question. So the way that this talk connects to this overall topic of this meeting, time in quantum theory, is that it's about the quantum structure of space-time. And what I will be emphasizing throughout the talk is the difference of a quantum theory or the quantum structure of space-time versus the quantum structure of space. And I think causal sets is a very nice approach to make that very clear. And I hope I'll be able to convey to you what the consequences are of thinking about the quantum structure really of the space-time in contrast to just space. And so the outline of this talk is roughly that I'll give an introduction to causal sets, assuming that you're not familiar with this approach to quantum gravity. And then I'll talk about a particular consequence of the main ingredients of causal sets, which are discreteness and space-time. And from that, we will actually get a particular form of non-locality that I will introduce to you. And then I will talk about some of the consequences of that. First of all, for the spectral dimension. That's a particular way of probing the dimension of a space-time basically through a diffusing particle. And then also talk about the difficulties and the progress that exists in recovering geometric information. So information about curvature invariance in a discrete space-time setting. And then depending on how time goes and how many questions there are in between, I might or might not get to talk a little bit about phenomenology and the implications that this whole discrete space-time structure has for a quantum field theory of a scalar field that would live on top of it. So let's get started with the introduction to the causal set approach to quantum gravity. So it's asking the question, what is the fundamental quantum structure of space-time? And then it starts from the general observation that very often when we quantize a classical system, we go from something that is continuous to discrete. For instance, we go from continuous spectra of the energy in classical mechanics to settings where we have discrete spectra of energy. And so causal set quantum gravity takes this as one of the starting points and says that this actually means that the quantum counterpart of the spacetime has to be discrete in some way. And so therefore we want to find a way to discretize spacetime, and the first question then is, how should we actually do that? The first idea you might have if you're asked to discretize spacetime is to do it in a sort of regular lattice type fashion, as we in fact often do in practical calculations. For instance, if we simulate systems, very often we discretize them on just a regular lattice. However, that will actually not work for quantum gravity because if you take a regular space-time lattice where you have just here a 1 plus 1 dimension example with one spatial dimension and time direction here, if you consider the same distribution of space-time points in a boosted frame, you will see that you have a sort of accumulation of space-time points along these lines, and then you have these voids in between where there are no space-time points. And that actually means that this whole setup of a regular lattice is not compatible with Lorentz invariance because there's a unique frame that you can easily distinguish, namely the one where the distribution of space-time points indeed looks like a regular lattice. And the other frame will have this structure with these more or less pronounced stripes. And because Lorentz invariance is quite well constrained experimentally, the idea in causal set quantum gravity is that we try to keep it at a fundamental level and therefore we can't use the simplest idea of how to discretize spacetime as a form of regular distribution. And in fact, it's not just a regular lattice that is excluded, but any form of regular pattern has this property that if you boost it, it changes what it looks like, and thereby you can always identify the original frame of reference as always a special frame. And so therefore, if we want to discretize spacetime but preserve Lorentz invariance, we actually have to choose a unique, a random distribution of spacetime points, because with the random distribution, if you boost it, then of course the placement of points will change, but there is no way to distinguish one or the other frame from each other because both of those just have a random distribution of spacetime points. And so this will be the starting point of causal sets. The very basic structure that we will be using is just a set of spacetime points that is randomly scattered into a continuous spacetime. This is the starting point to build the corresponding discrete spacetime. Now, of course, spacetime is more than just a collection of points. Spacetime carries a particular structure or geometry, and in the continuum, it is the spacetime metric that encodes that geometry. And the spacetime metric actually contains two different pieces of information. The first is on the causal structure, so on the light cones from a given point. The metric contains the information which points in the future and in the past of this point can be causally connected to those, maybe all inside or on the light cone. And then the second piece of information that the metric contains is a conformal factor, so basically a notion of scale that tells us, well, what is actually the actual distance to a point that is causally connected to this point in the origin. And just to be very specific, for instance, the Minkowski metric encodes the causal structure just in the sign of the line element. So whenever the sign of the line element is positive or zero, then there is a causal connection, otherwise there is none. And then the actual value of the line element, this is what encodes the conformal factor or the scale. And now, if we go to a discrete setting, of course, we no longer have a quantity like a metric, which is a tensor that is defined in the continuum that requires a tangent space to define it in order to make sense out of these space-time indices. And so we actually have to think about how this physical information that is contained in this tensor field, how this physical information can be encoded in a discrete setting like a causal set. And so the structure that we import and that will actually make a causal set more than just a collection of points is the causal connections. And we model them by just drawing links between any two spacetime points that are causally connected. So for instance, this spacetime point here in the center, this has a number of links to these other spacetime points. These are the ones that either lie in its past and can impact what happens at this point, or that lie in its future, where whatever happens at this point can impact what happens at this point. There are qualitatively different types of causal connections. There are the irreducible connections, so this is like a direct connection where there is no other spacetime point in this causal volume in between. Those are the irreducible causal connections. And then there's a reducible one, maybe in this example to this pink causal connection here. This actually follows because there is a causal connection between the point in the center and this point down here, and then another causal connection between these points down here. And so this pink link is a reducible link. It can be inferred from the other existing links. And so by changing a discrete collection of points into what actually looks like a network, a causal network, this is how you encode most of the pieces of the information in the metric, namely on the causal connection. And then we need to encode the information about the conformal factor, or the notion of scale or spacetime volume. And this, in this case, is encoded in the number of spacetime points. So in this random distribution of spacetime points into a continuum spacetime, the idea is that on average, you assign one Planck spacetime volume to each point. And so therefore, if you just count the number of points, and in this example here there will be 10 of those, then this translates into the number of Planckian 4 volumes or spacetime volumes. And so This then brings us to what is called the slogan of causal set theory that was coined by Raphael Sorkin, one of the pioneers of this approach. And the slogan is that order, in causal order, plus number, namely the number of space-time points, that encodes the geometry because that actually encodes the information that's given in the metric in a continuous setting. And so then this is an example of what an actual causal set looks like. So this is a causal set that corresponds to a sort of small chunk of 1 plus 1 dimensional Minkowski spacetime with a random distribution of points and all of the causal connections or the irreducible links drawn here. And so more generally, a causal set is actually just defined by 3 properties. So it's a very simple mathematical structure because it's really just a set of spacetime points, and it has one relation, namely this causal relation that's called precedes, and that satisfies just 3 properties. First of all, it satisfies that if x precedes y and y precedes z, then x also precedes x. X also precedes z. That's called transitivity, and that's something that causal order in any temporal ordering satisfies. So if I have a point in the past of another point, and then this line is in the past of the third point, then of course also the first point lies in the past of the third point. So this is also something that any temporal order, discrete or continuous, satisfies. Then the second requirement is something that we impose in order to make this discrete spacetime physically reasonable, and that is to require that there are no closed time-like curves. And so this means that if x precedes y and y precedes x, then these 2 points have to be actually the same point. And so in this way, you can't actually build a closed time-like loop that would allow you to travel into your own past. And so this is again a property that you would also impose in a continuum temporal ordering if you wanted it to actually be physically reasonable. And now it's the third property that really makes causal sets a discrete approach to to quantum spacetime, because it says that if you consider 2 points, x and y, let's say this one down here, and then this one up here, and then you consider all of the points that are causally in between those, and that would be, for instance, this point here, or this point, or this point, or this point. So if you sum up all of the points that lie in the causal volume between the point down here and the point up here, then the number of those points has to be finite. And this is what makes causal sets a discrete spacetime, because obviously in the continuum, if you would take a point down here and then a point further up in time, and then you look at the causal interval in between and you count the number of points, you'll get an infinity. And so this is what makes causal sets discrete spacetime. So how do you get to a causal set if you start out from a continuous spacetime? So there's a sort of recipe for construction that also underlies this plot here. You just randomly distribute spacetime points according to a Poisson distribution that is called sprinkling. And then you infer which points are linked by just using the continuum metric, which in this example here is a Minkowski metric. And once you have done that, you have constructed the full causal set, and you can just throw away the original continuum spacetime and forget about the coordinates at which these spacetime points lie, and the only structure that you keep is the points and the relations to each other. So what you're really keeping is just a discrete causal network of spacetime points. It turns out that the inverse process, namely if I give you a causal set and ask you what is the corresponding continuum spacetime that this could correspond to, then this is something that is currently not known. It's one of the big open questions of causal set theory. How do you reconstruct the continuum spacetime for a given causal set, and how do you even decide whether a given causal set actually corresponds to a reasonable finite dimensional spacetime manifold or not? Right, let me briefly stop to see whether there are any questions at this point. All right, so then let me continue.
Yes, there was a question. Why do you take a Poisson distribution? Could you take anything else, or is there anything important about this distribution?
Yeah, basically just because it's a distribution that you get if you have a significant, just a small enough density of spacetime points, But you could presumably think about some other ways of distributing spacetime, distributing the spacetime points. What the Poisson distribution allows you to do nicely is this relation between the number of points and the volume that you associate with that. So for the Poisson distribution, on average, you'll get 1 point per spacetime volume.
Maybe I could ask one as well.
Yeah.
So you use the continuum metric to decide which links should be there and which links shouldn't.
Mm-hmm.
But how do you decide which links are reducible and which links are irreducible?
So for that, I mean, you basically you can go through an algorithm where you basically take 2 points, let's say this one in the center and then this one up here, and then you're just asking, are there any points that are causally in between, which means any points that share a link with both of those, and with this point precedes this point, and then this point precedes this point. If you have a structure like that, and this causal relation between the point here and the point up here, that is implied by the existing links.
So that second link you just haven't drawn because you don't need to, because you've got these other ones here.
Yeah, so here I really just draw the irreducible connections, the links, and I don't draw all of the implied connections because that makes the diagram even more sort of cluttered. So you can think of the links that you see really as the nearest neighbors of spacetime points.
Is your definition of causation as the same as of signaling? Like the possibility of signaling?
It is related in the sense that it's always physically reasonable to think about a signal propagating along a link. So whenever there is a link between these 2 spacetime points, then that means that you can signal between those 2 points, and there is a causal connection between events on those points. Does that answer that question?
Yes, thanks. And I have a second question, can I?
Yeah.
Is your number of points infinite or can it be finite? I ask because of the randomness nature. Can you have something random that's finite or must be infinite?
So that depends on what space-time manifold I want to discretize. So in this example here, I'm just choosing a finite piece of 1 plus 1 dimensional Minkowski space-time, and the discrete counterpart of that just has a finite number of points. But if you think about really infinitely extended Minkowski space-time, then I would need an infinite number of points.
Like if it's finite, even though you have like initially a random distribution, being finite, I cannot always like find some row for the points and then find all the reference frame where these random, apparently random points are not that random. Does it make sense, my question?
Yeah, the question makes sense, and in fact, what happens if I take a space-time volume like this one, this sort of square, and if I boost it, then inside the volume I still get another random distribution, but of course the boundary here will also get boosted, and so the shape of the boundary changes. And so if I consider these sort of finite pieces of Minkowski spacetime, then because the boundary deforms, I do have a way of distinguishing different frames. So indeed, the statement is that either in infinitely extended spacetimes or away from boundaries, I can't distinguish frames because in there I have a random distribution. But if I have a boundary like this one, then this will deform under a boost, and so just by the deformation of the boundary, I could detect the frame.
Thank you very much.
All right, so then let's continue and talk a little bit about what really the space-time nature here implies, because the space-time nature of this discrete setting, in contrast to a discrete space, actually implies a particular form of non-locality. And you can see that by thinking about these links as basically the nearest neighbors of the point. So they are the points that are causally connected, but as close as possible. There is no other point in between. And if you think about nearest neighbors in a purely spatial setting, where you would, for instance, use the Euclidean metric, then the the contours of constant spatial distance to a point just form these circles, and so the nearest neighbors just are all within this compact region around the origin. And so we have nearest neighbors corresponding to the sort of local neighborhood of a point. And that's quite different from a space-time, because there the nearest neighbors are defined using a Lorentzian metric, and so points that are at very small forward distance are actually the points that lie on these hyperbolas and that approach the light cone. And that actually means that a nearest neighbor to this point down here can actually be very, very far up the light cone and very, very far away in just the spatial distance. And this is also what you sort of see in the actual causal set. Here you can see that many of these links are at nearly 45 degrees, so they are very, very close to the light cone. And you can also see that they stretch over a really significant or very significant extent within the space-time, right? So for instance, this point down here, it has a link to this point here that basically sort of covers half of the spatial distance that I have within this volume. And you can see many other links that cover really a substantial fraction of the maximal spatial distance. And so that means that because I'm looking at a discrete space-time, not a discrete space, I'm getting this form of non-locality where the nearest neighbors are not close by in a sort of intuitive sense, and where they are not in this compact volume in the vicinity of the point, but where the nearest neighbors can really be very far away in spatial distance. And so if you think about a causal set in terms of graph theory or in the language of networks, then this has particular consequences for the connectivity. It actually even means that the number of nearest neighbors is not limited, because you can always have a point that lies very, very far away, but it's super close to the light cone, so that its pore distance to this point here would be basically 0, but it will still have a direct link because there is no other point in between it. And so as you expand the volume, the number of nearest neighbors actually grows. You also have this non-local property that links can extend very far along the spatial direction. And this is actually somewhat reminiscent of so-called small world networks. So I'll get back to small world networks in a few slides from now. I would first like to talk about the spectral dimension, which is a particular way of measuring dimensionality, and which is directly affected by this non-locality which comes from the space-time nature. So the way to measure the spectral dimension is through a diffusion process. So just sort of standard continuum diffusion of a drop of ink in a glass of water. In the continuum, this is described by the diffusion equation, where P is the probability density for a point to diffuse to point X when it started out at X prime in diffusion time sigma. And this diffusion time now will not be the time coordinate in our space-time. You should think of this as some external sort of fictitious diffusion time. So this is not a physical process that we'll think about in our space-time. This will be a sort of mathematical process to plot the properties of our space-time. And this is interesting because in the continuum there's a solution to this differential equation that depends on the dimensionality d up here. And so if I look at the return probability, that is just setting x equal to x prime, and then I take a particular logarithmic derivative of that, I'm isolating this factor, this power up here, and so I'm getting what is called the spectral dimension through this definition, through this derivative of the return probability, and it corresponds to the topological dimension of the manifold. And so in practice, if you don't know what spatial dimension you live in, you could always find out through making an experiment such as this diffusion process. And now we do the same thing in a discrete setting, and so we start by thinking of diffusion on the graph, and we start by a regular sort of local lattice where the nearest neighbors are in a compact neighborhood around a point. And so then to model a diffusion process, you just have that the diffusing particle hops to any of the nearest neighbors with the probability given by 1 over the number of nearest neighbors. And so if you have a whole sort of cloud of diffusing particles, what happens is it spreads out through this network in this sort of local way. So in each step, if I just go back, I hope you can probably see it on the screen that the sort of these dark blue ink, quote-unquote, dots just spread from nearest neighbor to nearest neighbor. And in fact, at very small diffusion times, you can then see consequences of this discreteness of the network. But at large diffusion times, the spectral dimension then actually reproduces the dimensionality that this graph is embedded in. So in this case, it would reproduce 2. And now we do the same thing for this non-local type of network that is a causal set. This is a numerical simulation. Same idea as before, just with sort of red ink now. And now you can see that in very few sort of diffusion time units, so just after 5 or 10 steps of the diffusion process, the diffusing particle has already reached quite large spatial distances, and that is because there are these nearest neighbors that lie at quite large distances, and so in just a single jump, the particle can actually cover a large spatial distance. And so it basically spreads out along the light cones and then starts to fill in the interior of that space-time. And the fact that the particle can jump so far in just the first few steps means that the process spreads out much faster than it does on a regular lattice, and this is what is called super diffusion, so it's just faster than usual. And super diffusion means that the return probability changes very quickly, and because the spectral dimension is the derivative of the return probability, this leads to a very large spectral dimension. And this you can see in the beginning of the plot, so this is the spectral dimension as a function of the diffusion time, it just shoots up to large values. And then it will just continue to rise, and also the diffusion process will very quickly reach the boundary of the simulation if we would not play a trick, and the trick is that we impose an infrared cutoff, and by that I mean a maximal spatial distance that a single diffusion step is allowed to take. And so the diffusing particle is not allowed to jump right to the edge of the network in one step. We limit the spatial distance that it can jump. And in this way, at intermediate timescales, the non-locality then does not play such a large role, and there is a regime where the spectral dimension actually correctly measures the actual dimensionality that this discrete space-time corresponds to. In this case, this was just a 1 plus 1 dimensional example. And then at large diffusion times, the diffusing particle starts to reach the boundary of the simulation, and then the diffusion process equilibrates, and this is when you see the spectral dimension then dropping off. But the key thing really is that this non-locality of the network that comes from the space-time nature, that leads to a very large measure of dimension at small distances. And so one way to think about this is that sort of effectively, at least as seen from the point of view of the diffusing particle, a discrete space-time given by a causal set actually at small distances, so small diffusion times, has a very large dimensionality, and then only a sort of classical dimensionality on larger scales. And so there's really a sort of quantum gravity regime with very large dimension. And that's actually quite different to diffusion really on a discrete space. And so this is just to contrast with a quantum gravity approach that doesn't have the same space-time character and non-locality. And here, the spectral dimension is actually approaching the correct limit, which in this simulation here was 3 plus 1. It's approaching that from below, not from above. So before I continue, let me also stop to see whether there are questions on this point.
We don't have any questions in the moment.
All right, then I continue. Looking at this structure of causal sets from the point of networks, you might be reminded of a property that many real-world networks actually have, namely the so-called small world property. The small world property of networks basically says that if you choose any 2 random nodes in a network, there are very few steps that connect these 2 points. And actually, neural networks are also sort of a depiction of sort of how pages in the internet are linked to each other, and many other real-world examples actually feature this small world property. And you can imagine, right, for a neural network, it's actually important that it has not just sort of local connections, but it also makes these sort of non-local connections. This then raises the question whether causal sets somehow are similar to small world networks, or whether you could even think about causal sets as sort of maybe a model for something more complicated like a neural network. And to tackle that question, a few years back, together with one of my PhD students, we actually took a look at exactly that question. And we did that by looking at diffusion processes on actual data for neural networks. And this is actually for a particular fly for which the neural network is extremely well known, and so you can get data on how it is connected. And then you can look at diffusion processes on that network. And what you can see is that there are quite a few different types of curves. This is just because these type of networks are heterogeneous. So depending on where you start your diffusion process, the spectral dimension can look quite different because the neighborhood of some points in the neural network can look quite different from what the neighborhood of another point looks like. So if you take this sort of full collection of different curves, you can actually find sort of 4 different types of categories that they fall into. And one is actually exactly given by this behavior of what the spectral dimension behaves like in a causal set, where it first shoots up to very large values and then plateaus approximately at the correct sort of spatial dimensionality, which for the neural network is 3, because that's the dimensionality that the actual neural network of this fly is embedded in. And then you just drop off at larger values of the diffusion time. And so we found that that's quite fun, that these networks that arise in the context of thinking about discrete spacetimes, that they reoccur as sort of part of a real-world network, namely one with a small world property. And then we emphasize that the fact that it can mimic this network with a small world property is really because it has these non-local connections which come from the fact that we think of a discrete spacetime and not a discrete space. Alright, so let me now switch gears a little bit and go beyond measuring just the dimensionality of a causal set, but asking how can we actually extract more information about the actual geometry that this discrete causal set or this discrete spacetime is actually modeling. And that is of course motivated by the fact that ultimately we want to recover a description of quantum gravity, and gravity is of course encoded in the spacetime geometry. Now, if we were in a discrete space, then we would know how to encode curvature. Basically, you can encode curvature in if you do sort of discrete gluings or sort of discrete building of chunk, you can recover curvature in just something like the deficit angle about a point, as you can see in this sort of example here, where you just have a bunch of triangles that are modeling 2-dimensional chunks of space, and then you glue them together, and if you have a deficit angle, then you get positive or negative curvature. But now, the discrete space-time is this non-local type of network, and so a priori it's quite unclear where curvature is actually encoded. We can get a first idea by comparing causal sets that correspond to different spacetimes. So this is a causal set that corresponds to Minkowski spacetime, so a flat spacetime. This is a part of a causal set that corresponds to a de Sitter spacetime, so a spacetime with constant curvature. And you can see that these causal sets are quite distinct from each other in their connectivity properties, in that the number of links between these points up here is actually much larger than the number of links down here. And so that means that the way how causal sets actually encode geometry of spacetime or geometric information, such as about the curvature, is in the connectivity properties of these different spacetime points. Basically, in something like information about how many links does a point have, how many sort of second-order links does it have, so how many nearest neighbors, how many next to nearest neighbors, and so on. And so we'll now look at a more specific construction of exactly that. So the challenge if we want to recover information about the curvature is that we can't use sort of standard quantities from continuum spacetimes, such as the metric and the Riemann tensor and so on, because these have indices, and in order to define a spacetime index, we actually need a tangent space. And we don't have all of the structure from differential geometry in this minimalistic causal set setting. However, from these objects we can actually form scalar quantities, the curvature invariants, such as the Ricci scalar or the D'Alembert acting on the Ricci scalar, or also contractions of Riemann tensor and so on. These are scalar quantities, and so we don't need tangent spaces and a notion of spacetime indices to define them, but they do encode the geometry. And the way that the geometry is encoded is of course related to taking commutators of derivatives, because if I have a space-time curvature, then this means if I parallel transport a vector from one point to another along two different paths, then I'm not getting the same orientation of that vector. And so this is how curvature is related to the commutator of covariant derivatives, because it matters whether I first go in this direction and then in this direction, or whether I do it the other way around. And so therefore, in order to get information about curvature invariance in causal sets, what we will now want to do is construct some form of discrete operator that sits on a causal set and that mimics something that has two derivatives. So we take inspiration from thinking about a discrete version of the D'Alembertian of the scalar field on a regular lattice. If we had a regular lattice and wanted to evaluate the discrete counterpart of the D'Alembertian, we would just evaluate the field at this point in the center, and then subtract in each of the two directions, we would subtract the value of the field at the nearest neighbor to the original point, and then just divide by the lattice spacing. And so now we do the same type of thing in a causal set, but now of course the nearest neighbors are again the points that share a link with our original point up here. And then the next to nearest neighbors are those points where there's just exactly one point causally in between. So the next to nearest neighbors are the blue points. They all have exactly one point causally in between themselves and the black point. And then you can continue in this way to define causal intervals. So the next to nearest neighbors are the yellow points. They have exactly 2 points in the causal interval between themselves and the black point and so on. And so with this you can define a discrete operator that you call B that acts on a scalar field, and it just evaluates the scalar fields at a given point, and then it subtracts the value of the scalar field at all of the nearest neighbors, and then it adds the value of the scalar field at all of the next to nearest neighbors, and then it goes 2 layers and further. So these L's, those are sort of the causal layers. So you can think of this as nearest neighbors, next to nearest neighbors, next to nearest neighbors, and so on. And then you just divide by 1 over the characteristic length scale of a discrete spacetime, so basically by 1 over the discreteness scale. And then you can formally show that if you take this expression and you take the continuum limit, so the discreteness scale to 0, and then you also perform an average of this operator over many sprinklings of a spacetime, so many discretizations of the same spacetime, that this continuum limit of this sprinkling average, that actually reproduces the D'Alembertian minus 1/2 the curvature acting on a scalar field. So this sort of realizes this idea that curvature is somehow encoded in quantities that have 2 derivatives. And here we have built a quantity sort of along those lines, and the coefficients here are of course chosen exactly so that you get this correspondence in the continuum limit. And so if you now just choose a constant value of a scalar field, then this is how you can get back information about the spacetime curvature, essentially from the causal structure, because the only thing that was used here really is the links, so the direct causal connections, and then the next to nearest neighbors in a causal sense, and so on. We recently generalized this to higher orders by just starting from the idea that acting with this discrete operator B on a scalar field, that produces another scalar field for you, and so then you can act with this discrete operator again, and then you can actually formally show that if you really take the continuum limit of this expression, then you're actually getting a combination of Ricci scalar squared minus 1/2 times the Dell'Or version of the Ricci scalar. So this construction then gives you access to the second way to characterize the geometry. If you don't have a space-time where the curvature is just constant, but where the curvature changes, then this curvature invariant would be important to characterize it. Now, how can you generalize these type of ideas further? Basically, to construct the curvature scalar, we just used causal orders, so next to nearest neighbors, next to nearest neighbors. In this higher order construction, there's a slightly more complicated thing that came in that we call stacked causal orders, which takes the causal interval between 2 points and then adds the causal interval between the next 2 points on top. And so it is sort of this stacked interval of these 3 points that is actually different from the causal interval between x and z. And then you can imagine that you can generalize these type of constructions by basically generalizing the notion of nearest neighbors in an appropriate way. And so potentially by summing over these various ways to organize the causal information in the causal set, you could actually obtain further curvature invariants beyond those that were already seen. And yes, thanks for the signal that there's 10 minutes left. So this is basically an open combinatorial problem, how to actually arrive at higher order curvature invariants. So let me just very briefly stop to see whether there are any urgent questions at this point.
Yes, there is one question coming.
So this is probably a trivial question. So in your definition of this curvature in the Dell'Or version, so there's no dependence at all on the dimensionality there. It does work for whatever the dimensionality happens to be?
Yeah.
Or?
No, I wasn't very precise here. This is actually the expression for, I think what I wrote is the expression for 4 dimensions. So in fact, these coefficients here, they have to be adjusted according to the dimensionality. And so if you want to be able to calculate the curvature of your spacetime, you first actually need to measure the dimensionality, for instance with these type of diffusion processes, and then you can pick the correct discrete operator. So yeah, thanks for the question. And indeed, these coefficients here, they depend on the dimensionality. But they are also known for general dimensionalities. All right, so what I would like to talk about for the, oh sorry, was there another question?
Maybe we can continue and the person will ask the question again. So we'll have the first question.
Yeah, so as the last point to raise, let me raise this question, whether we can actually also recover spatial information from a causal set. Because a causal set, as I've been emphasizing, is very much about causal connections. So it does not very easily give access to information that is purely spatial. So more specifically, if I look at a continuum spacetime, just a 1 + 1 dimensional example, then I could draw a spatial hypersurface and 2 points on that hypersurface, and then I can of course calculate the spatial distance just from the induced metric on the spatial hypersurface. Now, in a causal set, the situation is more challenging because in a causal set, the links that I have are causal connections, and the very definition of the spatial hypersurfaces that points on that hypersurface are not causally connected to each other. And so if I find the analog of the spatial hypersurface in a causal set, then that is an anti-chain, and these black points down here are an example. So these are all points that are not causally connected to each other, and so therefore this is a collection of points that is a priori completely featureless. So in this drawing here, or in this sketch, you can of course see the spatial distances because I'm showing the causal set embedded in a 1 + 1 dimensional spacetime. right? But this is not information that is actually there in the causal set. So a priori anti-chain is just a collection of points with no connections between them, and so no features. And so this raises the question whether you can actually get back information on just purely spatial quantities. And so let's turn to the continuum again to see how actually we can use causal information to get back spatial information. And so if we look at the future light cones of these 2 points, then those intersect at some point. And so there's one point that is in their common future, but that is the first point to be in their common future. And then we can actually look at the space-time volume that is in the past of this common point, all the way down to the spatial hypersurface. And then the volume that this suspended volume that in this sort of peach color, that is proportional to the spatial distance between these 2 points, right? You can see that if you pull these 2 points further apart, then this suspended volume grows. And so this is actually something that you can recover from the causal information. And you can already see this in this plot down here. So we have the 2 points A and B. We are interested in their spatial distance. We look at their future light cones, which are given in a sort of light bluish color. Their future light cones intersect for the first time at this point down here. And then again in this peachy color, you have the volume that is in the past of this intersection point all the way down to the hypersurface. And this is how you can actually calculate how far apart A and B are spatially, just by using their causal structure. You can do a numerical test on that, and in this numerical test we actually kept the information on the spatial continuum distance so that we could see how well this reconstruction actually does. So what you see in this plot here is the difference between the discrete distance, and that is the quantity that is reconstructed purely from this causal information. And then we are subtracting the continuum spatial distance that we know, and then we plot this as a function of the continuum spatial distance. And so you can see that this difference drops to 0 at large enough spatial distance, which means that at large distances, this discrete causal way of reconstructing spatial distance is doing very well. You can see that at small distances, the difference actually shoots up. And the reason for that is that if you look at points which are very close together, and then you look at their future, then it's very unlikely that you will find a point that sits exactly at this sort of tip where the light cones intersect for the very first time. It's much more likely that there isn't a point here, but the first point comes a little bit further into the future. And so therefore, the suspended volume will be a little bit larger than what it would be in the continuum. And so this is why at very small distances, you see that this the discrete distance is larger. There's something sort of a more physical way that you can think about this, namely the statement that nearby spatial points actually decouple to some extent. So if you imagine the world lines of 2 observers going through point A and B, and then you wanted to know how long does it take until these observers can sort of first communicate with each other, then it turns out that in the causal set that takes slightly longer because there's basically vanishing probability that you have a point sitting right at this intersection of the light cones, and the actual point that connects them for the first time actually comes later. And so therefore, if you zoom in into the very small scale structure of discrete spacetime, you get this property of asymptotic silence that actually means that sort of world lines of distinct observers exist alongside each other and are in contact only later than they would be in a continuum. All right, so for reasons of time, let me actually skip the bit about the phenomenological consequences of some of these non-locality properties, and instead just summarize. So I've reviewed the causal set approach to quantum gravity, which is really distinct in the space of quantum gravity approaches in that it really takes the space-time bit very seriously, and it really builds a discrete space-time and not some form of discrete space that is sort of later wave rotation to space-time or something like that. And as I've shown you, by thinking about discrete space-time, we are automatically led to this very non-local type of structure. We have something that is a non-local type of network or a graph with very far away nearest neighbors. We therefore get a large spectral dimension, and we have some similarities with actual real-world networks that have the small mode property. And quite interestingly, despite the fact that it's a causal network with sort of very limited structure information, geometric information on, for instance, the curvature can be recovered from this causal information, and in a more maybe roundabout way, we can even recover purely spatial geometric information from the causal information. And so with this, I would like to thank you very much for your attention, and I'm looking forward to further questions.
Thanks very much for the very nice talk. So you said that the curvature is encoded into the connectivity properties, and I was wondering if this curvature needs to be finite or can it diverge like near a black hole, and how that network would look like.
Yeah, that's a good question. So typically, I think you would not recover something like curvature singularities like in a black hole, because in a black hole, at least if you're in a spherically symmetric case, the point where the curvature becomes infinite is really just a single point, namely the actual form. Right? And if you now imagine discretizing that space-time, then the probability that there will be a causal set element that sits at exactly this point, that is basically zero. And so therefore you would imagine that on a discrete version of a Schwarzschild black hole, the curvature would still become pretty large, but would never actually strictly diverge.
Thank you.
Another question before? Another question.
Hi, so I used to love causal sets, but now I don't understand anything and I feel super stressed out for some reason, so please help me understand. Okay, so in the representation that you're doing, I feel like there's need for a notion of distance between points to say that they're randomly distributed in the space, because if there's like normally if points are space-time, points of space-time, between them should be nothing, and it's impossible to have a certain amount of nothing. You should have only one point of nothing between points, which leads back to the lattice that you drew at the very beginning. And so at first I was thinking, okay, so it's good for you, because then you only have a lattice, you have your Lorentz invariant preserved, and it's good. You don't need all the things about randomizing stuff and something. But then actually everything is based on that, so that's why I feel stressed out. So, for example, that when you do this thing about the curvature, that you can see the curvature because the points are in your graph, they're closer, and like the density of points in your graph is not the same, but it's impossible if there's nothing between the points. So you are seeing a feature that is impossible. And yeah, sorry.
Yeah, thanks for the question. So in fact, what I've been using in these illustrations is that I still kept the embedding space-time that this causal set is embedded in, right? And so this allows me to say things like, okay, there is a random distribution of these points into my original space-time. But of course, the causal set itself.
Can you repeat? So these are not space-time points?
Say again?
These are not space-time points?
No, these are, the black dots are space-time points.
So the other points between the space-time points are also space-time points?
They are continuum space-time points that exist in my embedding space-time, but which, once I have constructed the causal set, I should actually throw away. And so this is just a graphical representation of the causal set that is embedded in a space-time. The actual causal set itself is really just the information about whether or not 2 points are connected. So one way to actually represent a causal set is through its so-called Hasse matrix. That is just a matrix that is filled with zeros and ones. So there's a 0 whenever there is no connection between 2 points, and a 1 when there is a connection between 2 points.
Yeah, we'll
so
provide
that's
that a lot.
actually the mathematical structure.
Yeah,
and what I've done in my talk is I very often used illustrations where the causal set was embedded in a continuum spacetime, and then of course there is a notion of various distances from that embedding spacetime, but that is not actually part of the causal set. And so you're also completely right in when I was introducing the sort of the ideas about the curvature here. Of course, I was also showing the 2 causal sets embedded in their respective continuum spacetimes, because that makes it even easier to see that they are different. However, if you would look at the Hasse matrices, so the connections of zeros and ones, and analyze how these Hasse matrices look, then you would also see a difference in the distribution of how many zeros and ones there are in all of the various rows. So basically in these connectivity properties, so how many other points is a given point connected to, which other points is it connected, what are its nearest neighbors or next to nearest neighbors. So in these connectivity properties, this is really where the actual geometric information is encoded. So here, I'm just showing you the illustration in the embedding spacetime, just maybe because it's more intuitive and easier to see than if I would have just shown you 2 matrices of zeros and ones.
Okay.
But you're completely right that this information on, for instance, the spatial distance here, that is not a parallel part of the causal set. It's just extra information in these illustrations.
And so just to be certain, so the curvature is actually something that you embedded in the connectivity, right? Because it's not something that emerges that you can see from the connectivity.
No, it emerges in the sense that this expression here, right, where you just evaluate some field, or even just a constant on this point, and then you just basically count the number of links, and then you count the number of next to nearest neighbors, the number of next to nearest neighbors, next to nearest neighbors, and so on. This is really just completely intrinsic information about the causal set. Nowhere here is there any information about an embedding. But this quantity actually reduces to the curvature if you evaluate it on a constant. And so the information on the curvature really emerges from the intrinsic properties of the causal set. So it's not something that I put in my hand. If I have a given causal set, then the curvature will take the particular value that is given by these numbers of links next to nearest neighbors and so on.
Sorry, I did not say.
Well, I have a follow-up question. Now, if you take a regular lattice to start with, and then you do your procedure, and in the end you throw away the space-time in which you embed everything, then you're left with a causal set, which is okay, right? And then you can ask yourself, what was the geometry that causal set came from? And that's a question you can't maybe answer, but you showed us. But would that be possible, that you do that way?
So if I would start with a regular distribution of points and then give the causal connections, that would mathematically also be a causal set. However, it would be a causal set in which I would break Lorentz invariance, because I can recognize that there's a special rank that is embedded in. And so that is a property that I don't want from the quantum gravity approach, simply because Lorentz invariance is very well constrained experimentally. There don't seem to be any violations of it. But it is true that in the mathematical space of all possible causal sets, there are structures that correspond to space-time manifolds with randomly distributed points, and there are also non-manifold-like causal sets that I cannot embed in any manifold, and then there are also some causal sets that have this sort of more regular structure. And the assumption is that if you can write down the correct dynamics for causal sets, which is a challenge that is an open challenge and that I have not discussed in this talk, but the idea is that if you can write down the right dynamics from this vast mathematical space of causal set, it would actually single out those causal sets that behave like manifolds and that have a random and Lorentz invariance respecting distribution of points. And all the causal sets that you can write down, of which there are very many, those would be dynamically suppressed. So this is what you would actually demand of the dynamics from causal sets, that it only actually singles out those causal sets that fulfill these physical requirements.
Okay, thank you very much. So at the moment, I give you a causal set. You can't tell me whether this respects Lorentz invariance in general.
So in general, it's not yet possible to do that because this sort of reverse way, this way of getting from a manifold to a causal set is known, but the reverse way of reconstructing the manifold from the causal set, that's an open challenge, right? And some of the quantities that I talked about, such as the dimension or the curvature, these are sort of diagnostics that you need in order to narrow down which manifold are you talking about. And so in general, this full sort of backwards reconstruction is not yet possible, and so therefore at the moment, if you give me some causal set, I can't actually tell you which manifold it corresponds to and whether it would correspond, whether it would embed it into a manifold in such a way that it would actually break Lorentz invariance. At the moment, that's not possible.
That's fine, yeah. Quickly.
Astrid is normally online. I think it makes sense
Sure,
to ask questions now
yeah.
and take short break.
Cool. Yeah, thanks for the nice talk, Astrid. I just had a curiosity since black holes were mentioned, so I thought I would ask. What is the statistical interpretation of black hole entropy in causal set theory? Is it some kind of configurational entropy associated with the links, or what is it?
Yeah, it's not yet fully understood. There are also some studies of what entanglement entropy on a causal set would look like. But in fact, one of the very motivations to discretize spacetime would be exactly black hole entropy, and would be the statement that, well, somehow black hole entropy seems to be well described by a setting where you just divide the black hole horizon into sort of little Planck area volumes, and you just put a 0 or 1 on it, which you could imagine being something like there being a causal set element or a link going through it or something like that. At the moment, though, there isn't a full understanding of what black hole entropy is really counting in terms of the different discrete causal sets that would correspond to a given classical black hole.
Thanks.
I would like to know, you build your causal set from a spacetime that's initially continuous and classical, right? Would you consider building a causal set from a spacetime generated by a delocalized mass, for example?
As long as you can give a spacetime metric, then you can build the corresponding causal set for that. A single causal set, in some sense, isn't really quantum yet. It's really just, maybe a better way to think about it is really that it's just a classical but discrete spacetime, right? And the quantum part really just comes in at the point where you would perform something like a path integral over causal sets.
I think we have addressed all the questions. Don't see any hands. So yeah, perhaps we should just thank Astrid again.